All right, in problem number 8, we're talking about a person that's on a swing. They have a mass of 60 kilograms. The swing has a length of 4.0 meters, so it's 4 meters from the center of rotation. And the tension that's measured in that swing is apparently 950 newtons, or 0.950 kilonewtons. Something that we should recall is that tension or apparent weight, which was introduced in last week's work, is the result of the sum or difference between gravitational acceleration and the acceleration experienced by the body in motion. Now, we're going to use a plus and minus sign here. I'm usually a fan of just always using a plus sign and letting the direction of acceleration account for the tension. And that works well when we're talking about ropes and pulleys, or as we saw with our skier example, if we had to, experience something like that when we had a theta value involved. But with rotational motion, it's a little bit more nuanced than that. We can handle that with angle measures, but to be perfectly honest, I think just taking a step back and thinking about what's happening realistically is more helpful here. So let me show you what I mean. If I know that the tension that's experienced by the rope, and so that we don't get confused with period, I'm going to use Ft for tension. That's our mass times gravitational acceleration combined with the acceleration experienced by the body. Now think about what's happening at the bottom of a swing here. If you've got somebody that's at the bottom of a 4 meter long swing and they're sitting right here, well, certainly they have a certain amount of weight force associated with being here on Earth. But as that rider comes swinging down, or as they're being spun in roughly this circular pathway, what happens to that acceleration, or the force that causes acceleration? Does that tend to increase the amount of tension that's experienced by the rope, or does it decrease the amount of tension? Well, in this case, the acceleration, the need to be center seeking here, actually increases the amount of force experienced by the rope. So hopefully that makes sense in that we have two forces or two accelerations involved here, and effectively two forces as well. The weight force mg, but also the acceleration force m times a. And those two added together sum together to make this total tension force. Now, the opposite would be true if we were talking about something that was kind of approaching the top of a circular path, like maybe you're in a car and you're approaching the top of a hill. When you reach the top of the hill, the acceleration inward actually makes you feel a little bit lighter. That's why you get that sensation in your belly when you go over a big hill or something like that. It feels you feel a little bit lighter in weight. So while your weight remains the same, mg stays the same, the ma actually would reduce from the parent weight, or the tension, if there was a rope in place there. All right, so let's see where we're going with this. Our goal for this question was to I'll find the person's speed at the lowest point. So I think in this case we might be talking about tangential velocity, although speed could be rotational velocity. I think this problem would be more interesting if we just go for the tangential velocity, the linear speed once we reach the bottom of this path. Okay, so let's see here. What do we know? We know the tension force is equal to this equation. The acceleration that's being experienced here is centripetal acceleration. So if we jump out to our course documents here and look for the definitions of centripetal acceleration, we've got one. Whoops, we've got one that'll allow us to isolate VT. Where did it go? Here we go. Our tangential velocity. So we'll use this definition, VT squared over R. And let's see, I'll write this. The tension force is mass times gravity plus velocity tangential squared divided by R. We have the G value, we have the R value, we have the FT value, we have the M value. We have enough to isolate VT. So the tangential velocity is going to require us to divide the mass over. Then after that's gone, we could subtract G. And after that's gone, we could multiply by R. And then after that's gone, we could take the square root. So a lot of little algebra here. If you're careful with it, you can do it all in one step. And when we substitute our quantities, the tangential velocity should be the square root of our radius, 4.0 meters, times our tension force, 950 newtons, divided by our mass of 60 kilograms, minus gravitational acceleration of 9.81 meters per second squared. Okay, so off screen that calculated out to be 4.91. Now a quick check of our units. Again, we had a meter for the radius. We're multiplying that by a Newton per kilogram minus a meter per second squared. So a quick check here. Let's see, these don't agree, so I have to make sure that they do. We have a meter, and all of this is under a square root too, by the way. So Newton is a kilogram meter per second squared. So a kilogram meter per second squared divided by kilogram, those units are going to cancel. And we are left with another meter per second squared, which is good. We can see that we can subtract those two, and a meter times a meter per second squared ends up being a meter squared per second squared, and the square root of a meter squared per second squared unit ends up being a meter per second, which is precisely what we were after. We know our setup was good, and apparently that rider is swinging at a speed of 4.91 meters per second. And the final question for this week's homework, we have a roller coaster, and the coaster's mass is 500 kilograms. The car has a speed, we'll call that a tangential velocity of 20 meters per second at A, and we would like to know the force that the track is exerting at this point. And then part B, what's the maximum speed the vehicle can have for it to not lose contact with the track up here? In other words, at what speed would it take for this thing to go weightless once we get to B? So I like this diagram because it does indicate that while the track itself is not a perfect circular track, for this little region right here, it appears to be circular. So when we perform our math at A, we can use our uniform circular motion equations. And same thing with B. The entire track itself is not circular, but for this region through here, it appears to be circular, and we can use our UCM formulas. So we'll make note that the mass is 500 kilograms. We have a tangential velocity of 20.0 meters per second. We have a radius at A of 10 meters, and we had a radius at B of 15 meters. So in question A, we're looking for the force. Now, in essence, the force that we're experiencing here is a combination of gravitational acceleration force and the force due to that rotational motion. So I'm going to use the apparent weight formula or tension formula, mass times gravity plus or minus A. So I'm going to say that the well, I'll use FA for apparent force, not to be confused with A as in the point A, although I guess that doesn't really make a difference here because this is the force experienced at point A. But that would be the object's mass times G plus A, and the A that we're experiencing in addition to gravity is the centripetal acceleration. I'm certainly using a plus sign here because the riders and the car would experience a higher force than just force due to gravity. So I definitely want to use the plus sign at the bottom of that hill. And I'll also note, since we weren't given acceleration, the centripetal acceleration could be our VT squared divided by R. Both of those quantities were given. So now I've got a formula set up for me to simply substitute and solve. The apparent force or apparent weight at that position would be our 500 kilograms times 9.81 meters per second squared, plus our 20 meters per second squared divided by our meters quantity. And this result comes out to be 24,900. 24,900 would be 2.49 times 10 to the fourth power. And then to be clear, we have kilograms units that are multiplying by meters per second squared minus meters squared over seconds, or over meters. Sorry about that. Meter, that's a velocity up top, wasn't it? So that's a meters per second quantity that got squared. So we have our kilogram unit and our, let's see here, meters squared over seconds squared divided by meters does turn into a meters per second squared. So we can subtract those two units to produce another meters per second squared. A kilogram meter per second squared is a measurement of newtons. So we see that the force at that position is 24,000 newtons, almost 25,000 newtons. Now in part B, the question's a little bit different, but we're still going to use the same weight force. Now I'm going to use FB, I guess, just to be consistent here. The force at position B is equal to mass times the combination of gravity and our centripetal acceleration. But this time when you're at the top of the hill, the centripetal acceleration is effectively working against gravity here. They're working to cancel each other out, so I'm going to put a minus sign in that position. Moreover, in order for us to lose contact with the track, we have to go weightless. Now, the term weightless doesn't mean that you don't have weight. It's just that you appear to have no weight. There are other forces that have effectively canceled your weight force. So the net force acting on you is your weight, but also the additional force in the opposite direction. So this number will come out to be zero. Will come out to be zero to indicate weightless, and we still have a mass. Oops, let me go back to my red ink here. We still have a mass, a gravity, and centripetal acceleration. I'm going to use this VT squared over R again, because the question was asking us at what speed would we have to travel in order to go weightless. So let's work to get VT by itself. VT by itself would be, well, this is kind of interesting, 0 divided by m, that's still 0. Then we can subtract g to the left side, so we now have a negative g. We can multiply by r, so negative g times r, but this was a minus sign, so we'll have to multiply that by a -1 or divide by -1 to turn this positive, and then take a square root on both sides to isolate VT. So how nice is that? We've done some math without any numbers. We've done some algebra without any numbers. The mass component disappears, so it appears that if our job is to calculate how fast you should be traveling in order to go weightless in a uniform circular motion path, all you need to do is take the square root of the gravity here on Earth times the radius of the path on which you travel. So that's quite simple. So to the solution we go. Square root of 9.81 times the radius, in this case we said was 15. A quick check here, the square root of a meter per second squared unit that multiplies by a meter unit ends up being the square root of meters squared per second squared. So good, that does come out to be a meters per second like we're looking for. And my calculator off screen is telling me that this math comes out to be about 12.1. So 12.1 meters per second. If that roller coaster was traveling faster than 12.1, then it would lose contact with the track. 12.1 is about 24 or 25 miles per hour, which doesn't seem all that fast to me. So hopefully the designers of this roller coaster are aware of this math, and maybe they've gone through some ways to mitigate the potential disaster. That's why you'll sometimes see roller coaster wheels that are on both the top and the bottom of the track. The track is sandwiched in between them, and also sometimes you'll see some braking systems as you approach a hill, especially those hills, or the peaks at the top of a hill. All right, so I think that takes care of questions 1 through 9. I hope you found these videos helpful. I do expect to be back in the classroom tomorrow, and we can discuss further when we're working on our lab. Thanks for watching.